Hello guys, welcome again to our ongoing series of nuclear physics. This is seventh video of this series. We are discussing the chapter nuclear structure and basic properties of nuclei. In this video, we are going to discuss the topic Rutherford's backscattering experiment. We have already discussed about this experiment in brief in our first video. Here we will discuss it in detail. We will explain the experimental setup, observations of this experiment and conclusion made on the basis of these observations. So let us draw schematic diagram of experimental setup of this experiment. In this experimental setup, a piece of radium has been placed in a lead block which has a narrow opening. This is a lead block. A piece of radium which is source of alpha particle has been placed inside this block. Radium is a radioactive material which emits alpha particles. Alpha particles are randomly emitted in all the directions and are absorbed by lead block except those which are going straight along the axis of hole. These alpha particles are then confined to a narrow beam of alpha particles. This narrow beam of alpha particles is then made to strike a thin gold foil. After scattering through this thin gold foil, these alpha particles are allowed to strike a fluorescent screen which is made up of zinc sulfide material, which is fluorescent material. Screen which is made up of zinc sulfide material. After scattering through this thin gold foil, these alpha particles strike this fluorescent screen where they produce scintillations. Scintillations are flashes of light which were produced when high energy radiation fall on fluorescent screen. This is central line from where we measure the various angles. These are scattered alpha particles. These are various angles made by scattered alpha particles. This is schematic diagram of Rutherford's backscattering experiment. Let us discuss the observations of this experiment. It was observed that most of the alpha particle went straight through thin gold foil. It shows as if most of the space of atom is empty. Some of alpha particles scattered through large angle. It shows that there is an entity which has positive charge so that repulsion occurs between alpha particle and this positive entity and large angle scattering is possible. And third observation was a very few number of alpha particle turned back towards the source itself. It shows that this entity is massive relative to alpha particle, so that if an alpha particle tried to collide head on with this entity, it turned back towards the source itself. On the basis of these observations, Rutherford proposed an atomic model in which entire mass of the atom and whole of its positive charge is confined in small central core, which is later on called nucleus. The small central core, later on called nucleus, which contain entire mass of the atom and whole positive charge of the atom. It is surrounded by negatively charged electron cloud and negative charge outside the nucleus is equal to the positive charge confined inside the nucleus. So this is the atomic model proposed by Rutherford. In this picture, most of the space of the atom is empty. Rutherford also supposed that if an alpha particle approaches positively charged nucleus having positive charge plus Ze, if an alpha particle approaches positively charged nucleus with positive charge plus Ze, it experiences an electrostatic repulsive force which is given by F 2E into Ze upon 4 pi epsilon naught r square. 2E is positive charge on alpha particle, Z is positive charge on positively charged nucleus, epsilon naught is absolute permittivity of free space, r is the distance between approaching alpha particle and this positively charged nucleus. This is equation 1. On the basis of this equation, Rutherford explained the observation of his experiment. From here, we can see that an alpha particle which is at relatively large distance experiences a very less repulsive force. So it went almost undeflected through the thin gold foil. Another alpha particle which is at relatively less distance experiences some repulsive force and it scattered through large angle. And if there is very rare chances that an alpha particle try to collide head on with the nucleus. If it occurs, then it slows down first and stops momentarily at certain distance from the nucleus. Then it turns back towards the source itself. Let us draw the picture of these observations. Let us say this is positively charged nucleus and these are negative charge outside the nucleus, electrons actually, negatively charged electron cloud outside the nucleus. This is beam of alpha particles an alpha particle which is at relatively large distance from this nucleus passed almost undeflected, or we can say that it went straight. Another alpha particle which is at relatively less distance, it scattered through large angle. There is very rare chances that an alpha particle try to collide head-on with the nucleus. If it occurs, then it slows down first due to repulsive force between this positively charged nucleus and alpha particle, and then it momentarily stops at a certain distance from the nucleus, and this certain distance from the nucleus is called distance of closest approach, and after reaching at this point it turns back towards the source itself. Distance of closest approach we will explain in the next video. This is undeflected alpha particle. So this is the picture of observations of this experiment. Rutherford also proposed a mathematical expression. For this, he made some assumptions. He supposed nucleus and alpha particle both are point masses and point charges. So first assumption was nucleus and alpha particle both are assumed to be point masses and point charges. The second assumption was large angle scattering is the result of electrostatic repulsion between alpha particle and positively charged nucleus. This large angle scattering is the result of electrostatic repulsion between alpha particle and positively charged nucleus. And third assumption was nucleus should be of much high atomic number. Nucleus should be of very high atomic number so that it should remain at rest. during the scattering of alpha particles. So these are some assumptions made by Rutherford to develop mathematical theory of backscattering experiment. He developed an expression, mathematical expression for number of alpha particles scattering at an angle phi in unit area of fluorescent screen which is placed at a distance r from the thin gold foil, which is given by n naught nt z square e square cosecant 4 phi by 2 divided by 16 pi square epsilon naught square m square v raised to power 4 r square, where n naught is number of alpha particles originally incident normally on the thin gold foil, n is the number of atoms per unit volume of the thin gold foil, t is the thickness of gold foil, Z is the positive charge on positively charged nucleus, and phi is the angle at which we are finding the number of particles scattered, and m is the mass of alpha particle, and v is the velocity, initial velocity of alpha particle, and r is the distance between gold foil and fluorescent screen. So from here we can see that number of alpha particles scattering at an angle phi in unit area of fluorescent screen are proportional to thickness of the gold foil, which is T square of the positive charge on the positively charged nucleus. It also directly proportional to fourth power of cosecant of the phi by 2, and it is inversely proportional to fourth power of velocity, initial velocity of alpha particle. Dependence of n phi on these four quantity experimentally verified by Geiger and Mercedin, and then this mathematical theory of backscattering experiment was adopted satisfactorily. Next topic we will discuss in the next video. Thank you.